the recording. Okay. So, God. Okay. So, couple things. Alex is due tonight, I believe, for the inverses module. Be sure to make sure you're keeping up with your Alex. And homework, I think we're on homework 5, was posted yesterday. Be sure you're getting that done by Friday. That is just on mainly trig inverses and a couple of problems with the triangle stuff we did yesterday. So you should be good to go. You should know everything you'll need to know for the homework at this point. Are there any questions on anything? You won't need any of what we are doing today for the homework, which is good. We're going to take a bit more of a chill day, look at something called vectors, and then we're almost done with content for the semester. We'll have one more topic after that, and then it'll just be exam 3 and we'll be good to go. So on that note, let's go ahead and get started. Sorry, my iPad is not. Oh, that's why. Hold on. I am not signed into my Zoom on my iPad, so it's not going to let me share my screen. 1 second. Sorry about this. I don't know why it signed me out. Okay. Cool. Invalid password. Nice. Nice. All right, let me try this one more time. I am so sorry about this. Okay. Did the dual thing. It's going to think about it now for a minute. Please. There we go. Okay. Now it looks like it's going to work. Okay. Now I will share my screen. We can get started. I am so sorry about that. Okay. Okay. So we're going to completely shift gears a bit from what we did last time when we were working on solving non-right triangles, i.e. finding side lengths and angle values for triangles that did not have a 90-degree angle, so we couldn't just use right triangle trig. We're going to completely shift gears from that and talk about something called vectors, which are a very important topic if you'll go on to either take some kinds of physics classes or any kind of linear algebra. If you're in a math engineering kind of major, you'll be dealing with these a lot later, but they have a lot of really cool applications in trig as well. So we are going to talk about them. But before we can really apply too much trig to it, we have to get some important definitions out of the way. First of all, what the heck is a vector? Well, in math, a vector is kind of an abstract concept that can be described many different ways, but the 3 key ones that we are going to be considering are the 3 here. And the first definition is the most geometric one we'll think about, which is a directed line segment between 2 points. Directed meaning it has direction. The way in which the line is pointing matters. It's not like if you're looking at the line y equals x, we don't think about it going one direction or the other. Vectors do have direction. And the 2 points are what we call the initial point. In other words, on the vector we have drawn to the right here, this would be the initial point, and the terminal point, i.e. where the vector ends, where the vector terminates. So those are the 2 points we like to consider. Another way we can think of a vector, rather than just thinking about it as a directed line segment, we can just think about it as a point on the plane. So rather than think about, oh, it's a line segment that starts here and ends here, we can think about, okay, let's just consider the point x comma y. We can just consider that to be the vector. And we can only do that when the vector is in standard position. In standard position, is when the initial point is 0, 0. It's about what we would expect it to be. We can have vectors that are off all the way over here doing something, but it's not in standard position. So that would not, we wouldn't be able to consider the ordered pair here the vector. However, if we were able to, if we moved this vector to standard position, like then this point could be how we define the vector right there. Okay. So we can think about it as a directed line segment, or if we're only considering vectors in standard position, a point on the plane. And when I say standard position, I should also know it does not matter where a vector is. If you've ever watched the movie Despicable Me, the villain Vector, he has the quote that's like, a vector has two things, it has direction and magnitude. Those are the only two things we need to consider. Notice that does not include location. So this vector right here is the same as this vector over here, is the same as this vector, same as this vector, is the same as this vector. Does not matter where the vector is. It only matters once I change the magnitude, i.e. the size, or the direction. So if you ever need to think about what matters for a vector, Despicable Me. It's useful, I promise. Anyways, so does not matter where a vector is. It just has direction. It matters which way it's pointing, and it matters how long it is. So that on that note, the third bullet point, a vector is any quantity that requires more than one number to describe it. The two numbers I'm talking about there could be direction and magnitude. Those are two different numbers we could use to describe it, and we will talk about those numbers. Also can just be described by an X and a Y coordinate. So we're not going to think about that third definition as much, but just know a vector requires two different numbers to describe it. Again, when you get to higher level mathematics, you can have 3, 4, 5. You can have many different dimensions of numbers you need. But in this class, we will only be focused on two-dimensional vectors in the plane right here. So what are some words we use to talk about vectors? What is some language we use? We talk about something called the horizontal component. And the horizontal component is just a really fancy way to talk about the x coordinate of a vector. And we can calculate it with this formula, r cosine theta. Now that kind of seems out of the blue, like where the heck, how'd you pull that out of your butt? Well, we've actually seen this formula a lot before. If we remember just from like first or second day of class, the cosine of theta, we calculate by taking the x coordinate over the radius. Let's multiply both sides by r. So we can determine the x coordinate by multiplying the radius by the cosine of theta. Cool, we've seen this before. This is just a different way to think about, okay, how could we find the x coordinate? If we're not given the x coordinate, how could we use the r, which is what we're going to call the magnitude here? So this is also the same as magnitude of v cosine theta. And if we have the angle theta made right here and that radius, we are able to actually calculate the x coordinate. Similarly, the vertical component comes from the same place. The sine of theta is equal to the y value over r. Therefore, y multiplying both sides by r is equal to r sine theta, i.e. the magnitude, that's the fancy way we're going to denote magnitude, sine of theta. So those are the two formulas for that, and I'll explain that notation for magnitude in a second, but those are the two we should be thinking about for horizontal and vertical component. That's just two different ways to write x and y. If we don't have x and y off the bat, but we are able to compute r and theta, we can use those. So r is what we call the magnitude, which is these absolute value bars around v. And I should note that the v with an arrow over it denotes that we're talking about a vector. If you see some number, some variable like that with an arrow over it, we're talking about a vector. We'll have vectors named w with an arrow over it, s with an arrow over it. Anything, if we have an arrow over it, that denotes that we are talking about a vector. So to find the magnitude, we denote just with the horizontal bars around the name of the vector, and we just compute it by x squared plus y squared, square root of that. This should also be familiar, because if we remember Pythagorean theorem, x squared plus y squared equals r squared. Take the square to both sides, r equals square root of x squared plus y squared. We consider magnitude to be the positive, so it's the net distance. So even if our square root could potentially, we normally have that plus or minus in front, We ignore the possibility of a minus here because we're always thinking of the magnitude as being a positive value. We're thinking of it being the length of a vector, and a vector will never have a negative length. So we only consider the positive for magnitude. And then direction, again, magnitude and direction, two things vectors have. The direction is theta. We think about the direction as being the angle theta away from the positive x-axis, thinking about the angle in standard position like we've been doing all semester. And to do that, because we have the easiest access to x and y coordinates usually, we will find this using tangent of theta equals y over x. Questions on any of this vocabulary? I know this is a lot all at once, so we are going to go ahead and get some practice with this. Also, just note, it's easy. It's nice to remember sometimes that tangent of theta equals y over x, that's also equal to a slope. That can be helpful when we're thinking about applying this to some real world context. So just always keep that in mind. Okay, so let's get a little practice with this. I want to write my vector v in standard position in component form. And what component form means is just kind of like this. Component form is just give the x coordinate, give the y coordinate. That is called component form. There's another form we'll talk about in a slide or two, but we'll get to that in a second. So this is the vector v here. We're given its initial and terminal points here. I also redrew v down here because, again, I can put v wherever I want it as long as I don't change the size or the direction of v or the magnitude of the direction of v. V is still v. So what I want to do is take v essentially and just move it down here. I want my initial point of v to go from -1, 4 down to 0, 0. So how should I think about it? Well, I need to consider what the net x distance of my vector is and what the net y distance of my vector is. And then whatever that change in x is and whatever that change in y is, those are going to be my two components. So how do we get net distance? How do we get the difference between two values? We subtract them. So to get the x component, I'm going to take 4 minus, or not 4. Yeah, 4 over here, my terminal point, minus the x point of my initial point, which is -1. So that x distance is 5. And then my terminating y point, which is 2, minus my initial y point, which is 4, that gets me -2. So v in component form in standard position is equal to 5, -2. Notice I'm using these triangle brackets here, these kind of less rounded triangle brackets. We use this when our vector is in standard position. Notice here we just kind of wrote them like ordered points. That's because our vector is not in standard position. But whenever our vector is in standard position, we use these things called angle brackets. They look like little triangle brackets. We use those to denote, hey, this is my vector. It's in standard position. That's what we were talking about on the last slide with a vector being described by a point on the plane and how it was written in triangle brackets up here. We do the same thing. Those angle brackets just to know, hey, I have a vector. This is its terminating point in standard position. Cool. Okay, so now I know what the vector is, 5, -2. So I can draw it out by going out to the point 1, 2, 3, 4, 5, 1, -2. And that is my vector. Again, it looks like all of the other two V's I've drawn, same length, same direction, they're parallel. However, I just moved it down a bit and had to do just a teeny bit of math to figure out where that is. Questions on that computation? Some other things to note just geometrically, and we will learn about computing these in a couple slides as well. I also wrote down the vector -v here. And all that did, notice that -v is the exact same length as v. All it did was just flip the direction of v. So geometrically, if we think about multiplying a vector by a negative number, we're reversing its direction. And then below it, I have 4/5 v. Notice it has the same direction. It didn't change. It's still parallel with the other versions of v I have. However, it's a little bit shorter. In fact, it's precisely 4/5 of the length of v. So if we have a negative sign multiplied out front, it changes the direction of the vector. And if we have any kind of number out front, this is a number we call a scalar because it's scaling the vector, then it changes the length of the vector. Multiplying by a number will never change the direction of the vector. Questions? Okay, just remember when we're computing these, we're looking for the net x and y distance. Okay. So let's talk about some more vectors and a different notation for vectors that we will often use. We just talked about component form, which is where we looked at something called 5, -2, where we just had the x coordinate and the y coordinate in standard position. That is the component form of a vector. But there's also this other form right here. This means the exact same thing, 5i minus 2j. These two vectors are the same vector. And essentially, what this other form is we take the x component and put it in front of the I here, and I'll explain why that works in a couple slides as well. And then we take this y coordinate and we put it in front of the j. So if I have the vector 4, 8, for example, in this ij form, below it would be 4i plus 8j. Or if I had the vector -1, -3, it would be -i minus 3j. Just taking those numbers and putting them as coefficients in front of the i's and j's. That's all there is to it. Okay, so those are two different ways we can write vectors. We will use them interchangeably, and you'll see some of them work really nice for certain different kinds of computations, just thinking about algebraically what's going on. So I want to find the magnitude and direction, i.e. this value here, the absolute value, well, vector b in absolute value bars, the magnitude, the length of the vector essentially, and the direction, i.e. this angle theta. So let's draw on our little picture over here what these values are. Theta is just going to be this angle right here made with the x-axis. It can also be, you can also think about it as being this. In this case, it honestly does not matter too much. It will probably just be easier to give this one right here. So I'm going to erase that guy. The length is just where we normally write r. The length is just whatever the length of that guy is. And we know this terminal point right down here is 5, -2. Okay, so how do I find the magnitude and direction? Let's start with the magnitude. If we remember from a couple slides ago, the formula for our magnitude is the square root of the x component squared plus the y component squared. Our x component is the 5. Our y component is -2. So that's just 25 plus 4 is equal to the square root of 29. And that is the magnitude. Just using the formula, plugging it in. Cool. Let's think about direction. Direction's a teensy bit trickier, but not too bad. On the first slide, remember, we are trying to solve for the direction using the tangent of theta equals y over x. We usually use tangent because it is the most accessible of the trig functions we have, because we usually have really easy access to both the vertical and horizontal component. So let's do that. Oops, where'd my slide go? There it is. So for the direction, we know that the tangent of theta is equal to y over x. Our y component is -2. Our x component is 5. Okay, so we're trying to identify what angle theta has a slope of -2/5. That's not a nice tangent value, I know, from my unit circle. So I'm going to have to use the inverse tangent function to get that theta is equal to the inverse tangent of 2/5. But remember, this has more than one solution. These always have two solutions. The angle -2/5 is a negative tangent. The inverse tangent function is defined in quadrants 1 and 4. The tangent values are negative in quadrant 4. So we're thinking about this vector, but this one also has the same solution. So we also have to consider that solution, which is just this theta down here plus pi. We always have to consider both possibilities for what theta could be. However, usually in cases of vectors, it's only going to be one of these solutions. And we have to think about that. Okay, which solution is it and why? Well, we're looking for this angle right here, which is an angle in quadrant 4. Oopsies. And this angle right here is the one down in quadrant 4, and that is given to us just by the pure inverse function. So we don't need to consider this solution in this case, but we always have to identify what both solutions would be so we could identify which solution we're looking at. If we had a vector over in quadrant 2, we would have needed that extraneous solution because it would not have been the answer in quadrant 4. So plugging that into my calculator, I get that theta, rounding to the nearest degree, is approximately negative 21 degrees. And graphically, you can see this makes sense. Our vector is about negative 21 degrees. It's about 21 degrees away from the x-axis into the 4th quadrant. And I think square root of 29 is a believable number for the length. Sounds about right. And again, that one's easy to verify because we literally just used Pythagorean theorem to calculate what the hypotenuse, quote unquote, of that triangle is. Questions on this? Okay, let's find the magnitude and the direction of another vector, just practicing this same skill. I want to find the magnitude and direction angle of the vector u give the exact value of the magnitude, and I can use my calculator for the angle. So before I do anything, I'm going to draw a picture of this because that picture is going to be helpful when we're trying to determine which angle we are looking at. So here are my axes. The vector has a x component of -8, so we're somewhere around here, and then a y component of +5, so we're over here somewhere. This is -8, 5. Cool, there's our vector. So we're trying to find this value right here, this radius, as well as theta, which theta here is going to look like that. Cool. I'm going to start with the magnitude because that one's always pretty easy to calculate. The magnitude is given to us by the formula square root of x squared plus y squared. So square root of -8 squared plus 5 squared equals the root of 64 plus 25 is equal to the square root of 89. Cool. There's our magnitude. Pretty straightforward, especially when we're just handed the x and y components. So now let's compute the direction angle. To do that, we'll use the tangent of theta, which we know is equal to the y component over the x component. Taking the inverse tangent of both sides, we see that theta is equal to the inverse tangent of -5/8. However, what could the other solution to theta be? Well, we know that the inverse tangent is defined in quadrants 1 and 4. -5/8 is a negative slope, so this is going to the one in quadrant 4 somewhere, but there's also the identical solution in quadrant 2. So, and this solution over here is just theta plus pi. So inverse tangent -5/8 plus pi, just to get over that pi radians. And I'm actually going to replace this pi with a 180 because I'm working in degrees and I don't want to get confused and only add 3 degrees to my final answer. I want to make sure that I'm adding 180 because I'm not working in radians right now. So which of these two solutions is it going to be? Is it going to be the one down in quadrant 4 or is it going to be the one in quadrant 2? Well, our vector is in quadrant 2. So it's not going to be the solution just given to us by the inverse this time. We are going to have to think about the one where we're adding 180 degrees. Plugging that into my calculator, I get that this is approximately 148 degrees. And this one's -32 degrees, which this theta right here is clearly not -32 degrees. So we can do the intuitive check that theta will be 148. Questions on magnitude or direction given x and y components? All right, let's see if we can go the other way. See if we can recover those x and y coordinates if we're given the magnitude and direction. So suppose we have some vector w with magnitude 26 and makes an angle of 200 degrees with the positive x-axis when w is in standard position. So let's think about what this looks like. draw my axes. I know it makes an angle of 200 degrees. Going just that is 180, so we need to go a little more to make 200. And we know the length of this guy is 26 because its magnitude is 26. I want to write W in the form W is equal to AI plus BJ. Now that requires that I find the X component, which is A, and the Y component, which is B. How can I do that? Well, if we remember from our first slide we did today with all those definitions, we talked about how we know that X is equal to R cosine theta, which is the same thing as the magnitude of W times the cosine of theta. Similarly, our Y component is equal to R sine theta, which is equal to the magnitude of W times the sine of theta. Cool. I have the magnitude of W, that's equal to 26. I know theta is 200 degrees. So I'm able to just, without doing any extra prep work, just use these two formulas to solve for X and Y components. So X is equal to 26 cosine of 200 degrees, which plugging this into my calculator is about negative 24.4. And then Y is equal to 26 times the sine of 200 degrees, which plugging this in my calculator is equal to approximately negative 8.9. Makes sense that we have both a negative X and a negative Y component because we are working in the third quadrant. Our terminal point down here is in the third quadrant. So we're going to have a negative X coordinate and a negative Y coordinate. That checks out. Beautiful. So only thing left to do is write W in that form. So W is equal to the X component, negative 24.4 times this vector I. And I'll explain what I and J is again in a little bit, minus 8.9 times this vector J. And that is your final answer. So just being able to work forwards and backwards with, okay, if I have the X and Y components, can I get the magnitude and direction? And if I have the magnitude and direction, can I work backwards, get the X and Y components? Okay. So let's talk about some operations we can do with vectors. Just like we can add and multiply numbers, we can add and multiply vectors. There's a couple different kinds of multiplication for vectors, and we will talk about two of those today. But first, let's talk about vector addition because it's fairly straightforward. So I have these two vectors, m and n, pretty standard vectors, and I want to find m plus n, the vector m plus vector m in AI plus BJ notation and in component notation. So this geometrically, let's think about what adding these vectors looks like before we do it computationally, because it's a little bit harder to think about geometrically, but the computations make sense. So my vector m is negative 3, 2. That lands me about right here. And my vector n is 5, negative 1. So it stretches out a little bit further and it goes down. What we're doing essentially when we add two vectors is we have the first vector m, and then what we're doing is we're taking n, putting the initial point of n onto the terminal point of m, and then what that computation tells us is, okay, where do we end up? What is this point right here? That is what adding vectors tells us. It basically is adding a vector is like stringing the vectors together geometrically and then seeing, okay, what is the terminal point of that? And to do that, we just literally add the components. We add the horizontal components of horizontal components and vertical components of vertical components. So thinking about it in AI plus BJ notation, we have that m is equal to negative 3i plus 2j, and n is equal to 5i minus j. Thinking about adding these together, m plus n in this form equals negative 3i plus 2j plus 5i minus j, We just add like terms. We add i's with i's, we add j's with j's, because if we think about walking along these vectors, m, we're going to go -3 in the x direction and then forward 5 in the positive direction. So we're going to walk backwards 3 and then forward 5. You can think about we're going to end up at the x point 2. So we have 2i. Similarly, y's, we can think about walking upwards 2 and then downwards 1. So we're going to end up with 2i plus j, which you can see adding like terms. Turns out that's exactly how that works. And then in component notation, this is just 2, 1. If we want to think about adding them in component notation, -3, 2 plus 5, -1, you would just add x's with x's and y's with y's. Questions on vector addition? Cool. Now, like I said, there are multiple types of vector multiplication. One of those types, and the type we're going to focus on this slide, is called scalar multiplication, because essentially what we're doing is we're scaling the vector. We're taking this vector v we have, and we're stretching and shrinking it by some factor. We're not moving it, we're not turning it, we're not doing anything to it with another vector. We're just scaling the isolated vector. So this in front is what we call in mathematics a scalar. And all this kind of multiplication we're doing is called scaling. That's why it's called scalar multiplication at the top of the slide. So how would we scale a vector? Well, I want to find -2 times the vector m. M is -3, 2, so it's something like this. So essentially what I want to do geometrically is flip the direction of m, so m is going the opposite direction, and then multiply it by a factor of 2, so make it twice as long. So geometrically, that's what we're doing. And we would do exactly what you think we would do. We would multiply both the x component and the y component by -2 to do this. So -2 times our vector m is equal to -2 times -3i plus 2j. Distributing that -2 out is 6i minus 4j, and that is your final answer. Again, this makes sense. This is at about 6, -4, which makes sense. We're on the positive side of the x-axis and the negative part of the y-axis. So intuitively, if we check with our visual, that terminating point 6, -4 makes sense. Questions on addition and or scalar multiplication? Okay, let's combine these two ideas and do something called a linear combination of vectors. And all linear combination means is we are adding vectors together in some form and they can be multiplied by scalars. That's all it is. We're just adding and subtracting vectors and sometimes multiplying them along the way. And it will give us one single vector in the end. So I want to find, oh my goodness. I want to find this vector -5u minus 3v, given that u and v are these two vectors. So let's just write this out, see what we're looking at. So -5u minus 3v is equal to -5 times our vector u, which is ai plus j, and then -3 times our vector v, which is 5i minus 6j. First, before I do anything with addition, I want to distribute out these scalars. Just distribute the 5 to its respective vector and the -3 to its respective vector. That's equal to -5 times 8 is -40i minus 5j minus 15i plus 18j. All I did was distribute out that -5 and that -3. Now, as you remember vector addition, we add like terms. So we add i's with i's and j's with j's. So our final answer is -55i plus 13j. And that is your final answer. Questions? Linear combination is just a fancy word for combining the two things we learned on the last slide, which is scalar multiplication and vector addition / subtraction. Okay, now let's talk about something that is going to be very useful in the context of trig, and that is called a unit vector. And a unit vector is just a vector with a length of 1. It's any vector, it can be pointing in any direction. All we care about is that it has a magnitude of 1. This should seem familiar to us. That means because magnitude is also what we've called radius in the past, that means the radius is 1. So a unit vector is a vector whose terminal point will land on the unit circle. If we're starting in standard position, the unit vector, regardless of what direction it's going, is going to have magnitude 1, i.e. radius 1. Therefore, it is going to land on the unit circle. Now, before we can even think about how to use these, how do we even create a unit vector? If I give you the vector, say, 1.5 comma negative 2.6, for example, that has a magnitude of 3, you can figure that out just by computation. How the heck could we take this vector that we know is of length 3, looks like this. We'll call that 1.5 comma negative 2.6. How do we take this vector that has length 3 and shrink it down to this vector here that's pointing the same direction, but just has a different magnitude? So computationally, how would I think about that? Well, I knew on the last slide to get m, or up here, 2 slides ago, to get m to be twice the length that it used to be, we multiplied it by 2. So what if I want v to be 1/3 of the length it was? Well, I would divide v by 3. That would get me so that v has a length of 1, because we knew to get v to 3 times its size, we'd multiply it by 3. So it makes sense to get v to 1/3 of its size, we'd multiply it by 1/3. This is always going to work with unit vectors. To create a unit vector, we always use the formula v divided by its magnitude. If we take v and divide it by the length of v, that'll get us to a vector of length 1. That will always work. If we have a vector of length 7 and we want it to be of length 1, we divide the vector by 7. That will get the length to be length 1. If we have a vector of length 243 and we want it to be a unit vector, we divide the vector by 243. That will get us a unit vector. This formula will always work. So let me do that. In this particular case, vector v divided by its magnitude, which is 3, is equal to 1.5 divided by 3, because we're component-wise dividing everything by 3, and negative 2.6 divided by 3, which is equal to 0.5 comma 0.86 repeating. You can do the math. You can check to see, is 0.5 squared times negative 0.86 squared equal to 1? It is. And that will always be a good check to make sure you've done your math right. Okay, now what if I want to think about finding a unit vector in the opposite direction as v? So I have v that's going that way. I know what my unit vector for that looks like. How would I find this vector? Well, remember from the first slide, all we have to do to reverse the direction of our vector is multiply it by negative 1. So this would just be negative 0.5, and then this is a negative 86 out here, positive 0.86 repeating. So the formula in general is just negative v over v. Again, just negating our unit vector. Questions on creating unit vectors? Now that we have this idea, there's 2 special unit vectors we can talk about that will help us to explain why we have this IJ notation for writing vectors. So, talk about 2 special unit vectors. This blank slide here just to draw a picture. So let's draw my coordinate axes. There's 2 special vectors we want to think about, and that's this one here that lands at 1, 0, and this vector here that lands at 0, 1. We call this vector 1, 0, we call it I. And we call this vector 0, 1, we call that J. Now, you may think, hey, we were using I's and J's in our previous problems. Why does that work? Well, let's think about the vector -3, 2 again. When we write -3, oopsies, -3, 2 in IJ notation, we write it as -3I plus 2J. All we're doing here is taking a linear combination of these two special unit vectors that I've named I and J. We're taking -3 and stretching this one out here. We're taking this vector 1, 0, and then reversing the direction, negating it. That's not what I wanted. And multiplying it by a factor of 3. And then we are adding +2 times our J vector. So we're taking this vector J here, scaling its length by 2, and adding that. And then we end up right here. That is what IJ notation is telling us. We're just adding linear combinations of these two special unit vectors. So that's where this notation comes from. Any questions there? Cool. All right, then let's talk about another form of multiplication we talk about with vectors, and that is called the dot product. So dot product requires two vectors to do, unlike where scalar multiplication, we only were talking about one vector. The dot product requires two vectors. I've changed the notation here a little bit. So I have the vector u equals u x component and u y component, and then v is equal to v x component, v y component. That's all those little fancy subscripts mean. And we define that dot product as the two x components of the vectors multiplied added to the two y components of the vectors multiplied. Notice that there's nothing with i's and j's in here. This is just a number times a number plus a number times a number. So we're just going to get a number out of this. Unlike scalar multiplication where we got another vector out, the dot product is just going to give us a number. We don't really understand what that number means at this point, but we will understand a little bit how it's computationally useful coming up here in the next few slides. But before we do that, let's just practice finding dot products and working with them. So I want to find the dot product of these two vectors, u and v. So let's follow the formula, work this out. U dot v, that's what this little dot is here in the center. That's how we denote the dot product with a dot. It's equal to the x component of vector u, which is 3, times the x component of v, which is -2, plus the y component of u, which is 2, times the y component of v, which is 1. 3 times -2 is -6, plus 2 times 1 is 2, equals -4. Again, notice this is just a number. Many of you may try to keep those i's and j's in there and spit out another vector. We don't care about this vector. That's not what we're going to talk about in this class. We don't care what -6i plus 2j's. We don't care about that vector. We just care about the scalar we get out. So we do not get a vector out of the dot product. Do not use the i's and the j's. Okay, let's see if we can work backwards now. I know that the dot product of this vector 6, 4 and 5, k, I don't know what k is yet. I know it's equal to 0. I want to solve for k. I don't really know how to do this just looking at it in this form right now. So I'm going to pretend like I'm taking the dot product of these two vectors, write that formula out, and see if it tells me how to solve for k. Well, I know the dot product is 0. How do I find the dot product? X component times x component. So 6 times -5 plus y component of the first vector, which is 4, times y component of the second vector, which is this unknown k we're trying to find. So I know that 0 is equal to 6 times -5, which is -30, plus 4k. I want to get k by itself. I can just solve for k now. So adding 30 to both sides, 30 is equal to 4k. And dividing both sides by 4, I get that k is equal to 30/4, which reducing that fraction is just 15/2. So you can work in either direction. With the dot product, you can take the dot product of two vectors and get out this scalar, which is going to be very useful in computing a lot of things with vectors. Or you can, if you know the dot product of two vectors, it A, sometimes tells you the information about some vectors, or B, if you're missing a component, you can work backwards to solve for that component. Any questions on the dot product? Okay. Well, let's see one way we can use this dot product, and that is to find, if we are given two vectors, we can use the dot product in order to find the angle between them. So the angle theta between two vectors, u and v, from u to v, so moving in a particular direction, can be found using this formula here. It's not given an angle theta equals, we know both, but we know that the cosine of theta is equal to the dot product of the two vectors divided by the multiplied magnitude of the two vectors. So let's see if we can use this formula to find the angle from n is this vector down here, up to m. So I'm solving for this theta here. Let's just move ahead because we know how to find dot products, we know how to find magnitudes. Let's see if we can use this formula to do this. Just to start, I'm going to do a little bit of scratch work to begin, so I'm not finding the magnitudes in my work. I'm just going to find the magnitude of m and n before I get going with the formula. I know that the magnitude of our vector n is equal to the square root of the x component squared plus the y component squared. So that is equal to the square root of 26. And then the magnitude of our vector m is equal to the x component squared plus the y component squared, the square root of that. So that's equal to the square root of 13. Cool. Plugging these into my equation and trying to solve for theta, I know that the cosine of theta is equal to m dot n, so that would be negative, or not negative, 5 comma negative 1 dot negative 3 comma 2 all over square root of 26 times the square root of 13. Doing that dot product in the numerator, 5 times negative 3 is negative 15. Negative 1 times 2 is minus 2 over root 26 root 13. So that's negative 17 over, I can pull a 2 out of that 26 down there to get 13 times the square root of 2. You may have to do a little extra math to see why that's 13 square root of 2, but that is how it simplifies. If we just multiply those two square roots together, we're able to pull the square root of 13 out. Since this is square root of 13 times 2, we can pull a 13 out front, and we're just left to square root of 2. Anyways, this is not our final answer. Normally at this point, I would rationalize the denominator. However, we know this is not our final answer. We do need to work a little bit harder to get there because this is the cosine of theta. So how do we find theta? Well, we use the inverse cosine function. So theta is equal to the arc cosine of negative 17 over 13 root 2. So we have a negative angle here. We know arc cosine is defined from 0 to pi. Theta here is clearly an angle from 0 to pi. It's not greater than 180 degrees. And in fact, it never will be. So we don't even need to consider the extraneous solution here. We just get to look at, okay, we know this angle between two vectors is never going to be greater than 180 because we're always going to look at the smaller angle. So because we're working with cosine and the inverse cosine function is defined between 0 and pi, we will never need the other solution. And that is just because arc cosine is defined from 0 to pi. That is the restricted domain of cosine that allows cosine to have an inverse. So the inverse of cosine's outputs will always be from 0 to pi, i.e. 0 to 180 degrees. This angle, theta, will always be between 0 and 180 degrees. So we never need to think about the extraneous solution here, which is kind of nice. So plugging this into my calculator and running to the nearest degree, theta is approximately 158 degrees. Questions on finding the angle between two vectors. Again, the main thing to recognize here is, although yes, this equation right here, cosine of theta equals all this stuff, does have two solutions algebraically, we're geometrically thinking about one particular angle. We're not thinking about two different angles. We only need to think about this angle theta between them, so we do not need the second solution, which is unlike when we're working with tangent, we do need to consider both of them. So if there's no questions, let's talk about some other things the dot product is useful in determining, and that's when vectors are perpendicular and parallel. So we want sometimes to determine when two vectors are perpendicular, and usually in applications, this is because perpendicular means we have a 90-degree angle, so something like this. And when we have a 90-degree angle, we can use nice things like right triangle trig, and we don't have to think about things like the law of sines and the law of cosines and dealing with that. Whenever we have two perpendicular vectors, math becomes much, much, much nicer for us. So we like when vectors are perpendicular. Another math word we use for perpendicular is orthogonal. For our purposes, those two words mean the exact same thing. So can you all hear me? My internet connection is unstable. It keeps yelling at me. Okay. Okay. Hopefully you all can hear me. If not, someone type in the chat or something. I don't know. Hopefully it doesn't disconnect me, but for now, I'll just keep going. Hopefully that works itself out. Okay. Anyways, so we know that two vectors are orthogonal. My audio keeps going in and out. Okay. If it gets worse, let me know and we'll deal with that then. I think it just reconnected. Spectrum is great. Okay. Anyways, so we know two vectors are orthogonal when the angle between them is 90 degrees. And remember from the last slide, that is just the formula that gave us the angle between two vectors. So when that angle is 90 degrees, they are orthogonal. And so this is the formula it gives to us. What is the cosine of 90 degrees? What is the x coordinate on the unit circle at the angle 90 degrees? It's 0. So we know that two vectors are orthogonal when this quantity is 0. Now, what does that exactly mean? How can we test to see when two vectors are orthogonal? Because that's kind of messy to look at. Well, note that both of these values in the denominator are going to be positive at all times. If they're 0, we don't have a vector. The vectors don't have a length, we don't have a vector. So that doesn't even make sense. And like we discussed at the beginning of class, the length of vectors are never going to be negative. We're never going to have a negative magnitude. So this denominator down here is always going to be positive. So we don't even need to think about that. We can multiply that both sides by that to get rid of it and just have that 0 is equal to u dot v. Now, this is an incredibly useful piece of information because what does that tell us? That tells us if the dot product between any two vectors is 0, that those vectors must be orthogonal, i.e. must be perpendicular. So to test for orthogonality, orthogonal vectors are such that u dot v is equal to 0. This is a test for orthogonality. So if I ever hand you two vectors and ask you, are they orthogonal? All you need to do is take their dot product. If the dot product is 0, they are orthogonal. Beautiful. If the dot product is not 0, they are not orthogonal. That's all there is to it. Now let's see if we can think about a test for parallel vectors. It's a little bit trickier to think about, but it works out pretty nicely. So we've all probably seen the word parallel before. Parallel just means that they lie on the same line. If they kept going forever and ever, they would never cross. They have the same slope, essentially. This happens when the angle between two vectors is either 0 degrees or 180 degrees. I don't like that there's an equal sign here because the cosine of 0 degrees is 1 and the cosine of 180 degrees is -1. So those two are not technically equal, but whenever we have this value equal to 1 or -1, whenever we have this value over here equal to that, we know that we have two parallel vectors. Now, it's not as nice to think about the formula to figure out a test for parallel vectors, so let's think about it geometrically first a little bit. Parallel means that they lie on the exact same line. They have the exact same slope. So i.e., if we put them in standard position, oopsies, see if I can do this actually. If I took these vectors here and moved them into standard position, they would lie on the same line like that. I know that's not great, but we can think about moving those vectors around. They would be on the exact same line in standard position, meaning they're scalar multiples of one another. So say we have two vectors u and v that are parallel. Oopsies. That means that u is just some scalar multiple of either some number, negative or positive, whatever, but there is some number we can multiply u by in order to get v. So if two vectors are parallel, such a number a exists. So if we're able to set that equation up and solve for a, then the two vectors are parallel. If some a exists that makes that equality true, they're parallel. So orthogonality, if the dot product is 0, they're orthogonal. For parallel, if we can solve the equation and solve for an a that makes that equation true, they're parallel. And if it's the dot product is not 0, nor is that true, then they're not orthogonal or parallel. Questions? All right, let's test these two ideas, work with them a little bit, and then we will do one word problem and be done for the day. So I have two vectors here, s and t. I want to determine whether they are parallel, orthogonal, or neither. So I want to think about which one should I start with here. Well, personally for me, computing orthogonality is a bit easier because I just have to do a dot product versus solving some kind of equation. So I'm just going to take the dot product of s and t, see if it's 0, and if it's not, and we'll try looking at parallel. So to test for orthogonality, I'm going to take s dot t, which is equal to -3 times -6 plus 2 times 4, which is equal to 18 plus 8, which is 26. Doesn't matter what it is, it's not equal to 0. So that's all we had to do. We got some number for the dot product of the two vectors that is not 0. Therefore, they are not orthogonal. We don't care what that 26 means. The 26, for all intents and purposes, means nothing to us. We just know that they're not orthogonal. So let's check to see if they're parallel. To check to see if they're parallel, I can set up the equation, the vector t is equal to some scalar times s. And I want to see if there's some scalar a that makes s equal to t. If there's something I can multiply s by, in other words, to get it equal to t. If there's some way I can stretch or shrink s or flip or do whatever. So what does this mean? This means that I want -6i plus 4j, that's just t, to be equal to a, some scalar, times s, which is -3i plus 2j. Multiplying that a out, this is the same as saying -6i plus 4j is equal to -3ai plus 2aj. Okay, so what does it mean now for two vectors to be equal? Well, it means that the x components must be the same and their y components must be the same. i.e. -6, the x component over here, must be equal to -3a, and 4 must be equal to 2a, the two y components. Let's solve for a on both of these. Here, I divide both sides by -3 and get that a is equal to 2. Here, I divide both sides by 2 and get that a is equal to 2. These two solutions match. That's what we want. That means that we can plug a 2 in right here and make s equal to t, i.e. if we scale s by a factor of 2, we get t, so they lie on the same line. T is just a stretched out version of s. You can think about it like that. So these two vectors are parallel. S is just half the length of t. If I got a equals 2 and then say a equals 15 over here, we would not have one solution that works. There is not one a value that makes these two x and y components equal, so then they would not be parallel. But because these two solutions match, we have two parallel vectors. So s and t are parallel because t is equal to 2 times s. Questions on orthogonality and parallel tests for vectors. Okay, so let's do one more. We'll start a word problem for today, and then we will have 2 more word problems to talk about with vectors on Friday, as well as the last topic we're going to discuss in this class, which is something called polar coordinates. It's another way of thinking about and graphing trig functions. So I want to talk about a little bit of physics because, like I said, these kinds of ideas with vectors are really useful for physics. So a shopper pushes a cart with a force of 50 newtons, that's what that N is, at an angle of 37 degrees from horizontal. We're not children, we're not at eye level with the cart, so we're not going to just be pushing it straight forward. We're going to be pushing down and forward on it. So we'll have our force going at an angle rather than just straight horizontally. So that's what that angle of 37 degrees is. I want to find the force vector in the form AI plus BJ. So this is how it always is. The force in physics is the same thing as the magnitude. So our magnitude is 50 newtons. That's what this value right here is. That tells us the magnitude. Force, magnitude mean the same thing. And our angle, theta, is 37 degrees, but notice we're going 37 degrees downwards. We're going downwards into quadrant 4. So theta is actually negative 37 degrees because we're not going positive 37 degrees. We're not pushing upwards on the cart. That would not make sense. Cool. Remember that slide where we had the magnitude and the direction and we were able to solve for the x and y components using the formulas magnitude of the vector times cosine theta and y equals magnitude of the vector times sine theta? That's all we need to do here. All we're trying to do is find the force vector in this form. What's required for that form is the horizontal and vertical component, which we achieve by using these two formulas, both pieces of information which we have. So let's go ahead and do that. So x is equal to 50 times the cosine of our angle negative 37 degrees, which is 39.9. And then y is equal to 50 times the sine of negative 37 degrees, which is equal to negative 30.1. Intuitively check, this makes sense. Our x vector is positive, so yes, we are pushing the shopping cart forward in a positive direction. And our y component is negative. We are pushing down on the cart in a negative direction. We're not putting any force upwards. All our net force is going downwards. So these two answers intuitively make sense. So our final answer for our force vector is 39.9i minus 30.1j And we want to think about, are there units on this? There haven't been units on any of our vectors yet, but are there units? And there are. We're talking about a vector that describes the force, and the force is given to us in newtons, as given up here. Because you remember, we keep the unit Newton attached right here and the unit of Newton attached right there. So we have we're moving 39.9 newtons in the x direction and negative 30.1 newtons in the y direction. So the unit on this entire force vector is just newtons. And if we think about this physically in the real world context, this means the only real component that matters here is the x component. The y component doesn't do anything. If we just push downwards on a shopping cart, it does not do anything. So the only component that's really driving the cart here is the horizontal component, because that's what's pushing it forward. So if I asked you to find at what it's being pushed down at 50 newtons, what force is the cart being pushed forward with? Your answer would be 39.9 newtons. It would be the horizontal component of this equation. Any questions on this word problem? Okay, we're going to expand on this shopping cart problem a little bit more in class next time. But for now, I think I'm going to stop here. This is a nice stopping place. There's not any of this vector stuff on your homework, so if you're still a little confused, that's okay. We'll do this and another practice problem on tomorrow's Friday, and then we will wrap up with polar coordinates. Otherwise, I don't really have anything else for you today. If you have any questions, feel free to stick around, but otherwise, I hope you'll have a wonderful Thursday, and I will see you all tomorrow.